Welcome to week 4, Graduate Statistics, University of Cincinnati. This is video 4 of this week. So variance, we finished the previous video saying that in addition to the shape of the distribution, the center of distribution, we can also and should get measures of the spread of the distribution, because that would speak about the precision of the point estimates of center. Now, variance is one of the ways we can estimate this spread, and that's roughly the average squared deviation from the mean. So just like we have a different symbol for sample mean and population mean, we also have different symbols for sample variance and population variance. This is this very ugly equation that expresses how it is that we compute the square deviation from the mean. That's the symbol for sample variance. This is the symbol for sum, and it's telling us that we need to sum a bunch of observations beginning from observation 1 and going all the way up to observation n, with n equals the sample size, right? So here we have xi representing each one of the observations. So we are going to do subtract each one of the observations from x1 to xn from the mean. We do the subtraction for each one of the observations and we square them. And then what we'll do, we'll sum those squared deviations and divide by n minus 1. Pretty much an average, right? We're taking these differences between each observation and the mean, we're summing them up and divided by the number of observations minus 1. It's a little correction that I can tell you more about if you'd like to know on the live session on Wednesday. Now, if you have the center here, which is the mean, now what you would have to do is to get each one of the observations that are inside of each one of these beans and measure the distance from that center by computing that difference. Because some differences are positive and some differences are negative, we square them so that they're all positive, because we want an absolute average of the deviations around the mean. So let's do an example. The sample mean is 67.12 for the life expectancy in the 1900s, and the sample size is 179. Now, what do we have to do to calculate the variance of life expectancy in the 2000? The sample mean of life expectancy in the year 2000 is 67.12, and the sample size is 179. So how do I compute that? So let's look. This is the first observation, that's xi, x1. So we subtract x1 from the mean to see how deviated that observation is. We square it. We take the second observation, we subtract from the mean to see what's the magnitude of the deviation of the second observation from the mean. We square it. We keep doing that all the way to the last country in our data set, which is 47.9. That's the xn, or the x, in this case 179, and we subtract that from the mean and square it. All right. So variance, zoom in on the calculation. What is the variance then? We're doing all of these deviations from the mean and squaring it, summing them all, and divided by roughly the number of observations, with a little correction, as I said. So really, roughly, we have the average squared deviation from the mean. Why are we talking about deviations? Because we're getting a measure of spread, how spread out those observations are from the mean. So mathematically, when we want to compute spread deviation, we use subtraction, which is why we're doing the subtraction here. Again, you might be wondering why the squaring. All the squaring is to make every one of the deviations positive. That's the reason. So the thing with variance is that you end up with a measure that's not in the scale of the data because you're squaring everything, right? To make everything positive. Now, because I'm getting this 95.75 years of deviation around that 67.12, it's like, oh my gosh, there are life expectancies that go all the way up to 67 plus this value? No, because it's not on the scale of the data. Then why do we use the square deviations in the calculation of variance if we then end up with this silly measure that is not meaningful in a sense? And I already mentioned we use it to get rid of negatives. So observations equally distant from the mean to one side and the other don't cancel each other out and are instead equally weighed. So this is one of the reasons. But if you are a mathematically inclined person, you might be thinking, but well, we can simply take the absolute value of the difference. Why are we squaring and creating this problem that we end up with a measure of spread that is not easily interpretable? Well, there is a reason. So sorry, this is just an illustration of what I just said here, that if we don't square it, we would have, if we compute the deviation of this score from 0, it would be -2. And if we computed the deviation of this score from 0, it would be +2. And when we summed them up, we would get, we would get a measure of spread that equals 0 for every symmetric distribution, because you can think about the same calculations happening for every one of the scores on one side and the other. But if we square and then sum, then we have a value of spread that's not 0. And the two observations, the positive and the negative, is equally weighed. So again, this getting rid of negatives thing, we could have done it by simply saying, okay, the deviation is -2, I would just use 2. I'll get the absolute value. Ignore the sign. Same here. Why don't I just do that? Well, the reason is that when we use the square deviations to compute our spread, we're penalizing more the large deviations. So if you have just tiny bit deviations around the mean, we don't want to, the variance does not penalize as much those small deviations as it penalizes the larger ones. And that's sort of important because when we measure things in the real world, some variability is also always in there by pure chance. So small deviations shouldn't be as critical for getting a measure of reliability and consistency, precision of the estimate, as when you have values that are more deviated from the center. So that is what variance really does. It allows us to kind of weigh more the values that deviate more from the mean than those small deviations that could be less meaningful. Now, how do we solve the problem that we end up with something that's not meaningful? Well, we solve the problem by having a measure that is in the scale of the data and at the same time does the nice thing of penalizing more the deviations that are large, which is the standard deviation. While the variance, we compute the square deviations of every observation from the mean, then we sum them all, and we divide by the number of observations minus 1. And we end up with this thing that's too large because they're all they're the averaged square deviation. To bring it back to a meaningful scale, standard deviation is simply the square root of the variance, right? So we end up with something that's too large because it's the square deviations. If we take the square root, now you have the standard deviation, which is in the scale of the data set. So it has the same unit and is meaningful. And we also have a symbol for the sample standard deviation. If you noticed, variance is s squared and standard deviation is just s because it is the square root of variance. And the population standard deviation is just sigma. instead of the sigma squared. So the standard deviation of the sample is simply the square root of the variance. So here in our example, if the variance was 95.75, if we take the square root of that, now we get a value of spread that is nicely in the unit of the data. So we know that we have more or less a 67.9 average of life expectation plus or minus 10 years as the spread. Now, it's important that you know too that approximately all of the data of a symmetric distribution will be within 3 standard deviations of the from the mean, almost 100%. So before we go to the interquartile range, I want to say one little thing more about standard deviation. That we're saying that about 100% is between the mean plus or minus 3 standard deviations. But if you think about the mean plus or minus 1 standard deviation, you have about 67% of the data in there, right? If you do the mean plus or minus 2 standard deviations, you have about 95% of the data in there. If you do the mean plus or minus 3 standard deviations, as I said, almost 100, closer to 99%. Okay, so you know more or less based on the standard deviation how much data is encompassed in that little range if the distribution is symmetric. Now, the interquartile range is another measure of spread that I told you we can use. And that is the range of the middle 50% of the data, or the distance between the first quartile, 25th percentile, and the third quartile, the 75th percentile. So here's the median. So it's a measure of spread around the median. So when you decide that the median is the best thing to use, the measure of spread that you want to choose is interquartile range. So here is the median. Here is the 25th percentile. Here's the 75th percentile. And interquartile range is the difference between these two scores. That will then grab the mid 50% of your data set. So the 25th percentile is also called the first quartile, or Q1. The 50th percentile, as you know by now, is called the median, and the 75th percentile is also called the third quartile, or Q3. So between Q1 and Q3 is the middle 50% of the data. The range these data span is called the interquartile range, or the IQR. One more time with filling, IQR equals Q3 minus Q1. We'll come back to discuss more on our next video. See you then.